All right, so I'll talk about work with a number of people, but I want to single out, I guess, a lot of this is driven by Dylan Foster. He was a postdoc, and the latest results are driven to a large extent by Fan Chen, who is a second-year PhD student. So there are course notes here. At some point, hopefully, it will become a book, and we'll be updating these over the next half year. Okay, so let me start. What does this talk about? Kind of a classical machine learning is, at least when I grew up, it was you have passively observed data, and now you fit some kind of model, and this includes problems like image classification, speech recognition, translation, and so forth. You train model on passively collected data. In many modern problems, I want to argue, we're faced with actively gathering information. We're faced with decision making, where our decisions influence what kind of data we receive. And examples here are clinical decision systems, recommendation systems, robotics, games, and more recent applications are fine-tuning of LLMs. So these are all active procedures where if you're not smart about how you collect data, you might not get what you want, right? So I think there's a lot of opportunity here to develop both theory and practice of kind of this active gathering of information. Okay, so a little bit more mathematics. So I'm thinking of a repeated interaction between the agent, learning agent, and the environment, which proceeds over capital T rounds, and little t is a discrete time step. So over discrete time steps, one by one, the decision maker is receiving a context xt, makes a decision pi t. I will say decision or action interchangeably, and then receives some kind of reward and maybe some more information than the reward. Maybe there's some kind of observation OT at time t. Okay, so examples of this are abound. Think of a doctor, finished medical school. Now, a new patient comes to the doctor. The doctor observes the context, observes the medical history and the current symptoms of this patient, and needs to select a treatment, pi t. After the treatment, maybe later, the doctor receives the reward, naturally, whether the person got better. But there is also more than just reward. There is some kind of a trajectory of how the person got better that could be informative about the problem, right? So it's not just about reward maximization. It's going to be also how to take into account these observations. Okay, so of course, if you're doing personalization, if you're one of these companies, you have a user that comes to a website that provides you context, whatever you know about the user. The system makes a decision pi t, and then observes whether the person, let's say, clicked or purchased an item. And maybe there's some additional observation, like behavior of the user. But I would like to start thinking about these decisions, in fact, not as, in this case, not as just, 400 milligrams of ibuprofen or Tylenol, whatever, paracetamol, whatever you guys have here. But these could be very structured decisions, right? So this itself can be a decision tree, or it can be a policy. Start doing this, and then if the patient does this, then do this. This could be a decision tree. This could be a policy. Then this observation OT is especially important because you want to see the whole trajectory of when you did this, what happened, when you did this, what happened, and so forth, not just the final outcome. So I am thinking of decisions pi t as a very high-dimensional, very structured object. Here is another example. If you're fine-tuning your large language model, let's say this is a kind of a before releasing the large language model. So XT, the context is a prompt of the user. You're fine-tuning the model. You have a prompt of the user. you make a decision which is now the answer to the prompt. Okay, so the whole answer. Let's say this is a math problem. This is your the solution, and then you receive rewards. So people talk about verifiable rewards for large language models, right? Whether the problem was solved correctly, okay, in certain cases, although this is not typically done, but there could be observation of the whole, something more about the trajectory. You can have rewards for intermediate stages, for instance, right? So there is more than just the final reward. Okay, now the problem that, as stated, in fact, so general that it subsumes episodic reinforcement learning, in the sense that my actions pi t can be policies. I put into a robot a policy. I release the robot for this episode. The robot goes and collects trajectories, collect reward. You have a trajectory. The robot comes back. We update the policy, right? So the pi t, the decision, is actually the whole policy. And then OT, this observation, is the whole trajectory of state action reward triples, right? Okay, the question is, can we solve this problem at this level of generality, given that it subsumes RL and we just had a Turing word, given for RL, so we have to be a little bit modest about our goals, and this is just a mental picture that I would like you to keep for the duration of the talk. I don't know how well this is coming. It's pretty good. So there's a space of context, right? So these are medical histories of the person. Of course, these are, again, this is one axis, but this is a high dimensional structured axis, right? And you have decision, which is also a highly structured object, right? And then for each context and each decision, you have some mean reward, right? So for instance, if context is the a prompt to an LLM, and decision is what you output as an answer, then there's some mean reward that is natural, right? Is the solution correct or not? If you consider verifiable math problems, then it's either correct or not correct, let's say. Then this whole surface is kind of a complicated 0-1 surface. But you can imagine more finer details like partial answers and things like this. Right, so this is a kind of a complicated surface, and when we're faced with a certain context at time t, we're looking at the slice for that context, right? A slice for that context, and now we have to choose a decision, right? That's the order of making these choices, and we select one decision. Of course, we don't know this surface, right? If we knew the surface, somehow the problem might be easier, but we have some kind of weird access to this. We get to query, right? We're being put into some context by prompting the LLM. Then we make a decision, and then we observe the outcome by verifying the correctness, right? And so you see that it's important how do we choose these decisions, because that's the only number that we're going to see, right? When a doctor prescribes medicine, they will only see the outcome for that prescription, right? They will not see the counterfactuals, the other outcomes, right? So that's important, because in the previous way of kind of the old style of thinking, is you have IID data collected and you do some kind of least squares, ERM, and that's your solution. But in this dynamic or interactive way of thinking, you really have to be thinking about how much information this brings, this new decision brings about the problem. And we need to start thinking how this information propagates throughout the graph, right? Throughout this. Okay, so again, just to say this again, the data that we observe comes not IID, but from a distribution that is sequentially induced by us, right? That's the difficulty. Okay, and then at the next round, you're going to have another slice, of course, and you choose this decision, you observe the outcome, and so forth. And okay, we were discussing with Nicholas yesterday. So, if you given a prompt, if you keep sampling answers, right? Well, you have some estimate of this model. You don't have the actual model. You keep sampling, and you receive some rewards, right? But if you don't do some kind of active exploration, you're stuck with the things that you are putting weight on, right? If your model puts very low probability on a good solution to a math problem, then it will take you forever to surface that just by sampling if you don't do active exploration. All right. Okay, so this is the outline of the talk. We'll talk about structured bandits. So what is structured bandits? It's just this slice. So I'm just going to pretend that I'm going to receive the same context again and again. Same person comes, right? So we're just looking at this slice because to solve this whole problem, we need to solve the one slice problem first. So that's going to be called structured bandits. We'll set up the problem. We'll ask what's wrong with being optimistic, my favorite motto in life. Then we'll talk about a certain solution, decision estimation coefficient. We'll talk about the contextual bandit extension. And then if there is time, I'll show that this, in fact, is a much more general kind of field in which one can make kind of contributions related to statistics. Okay, so to set things with the mathematical notation, you have a decision maker for capital T rounds. At each round, selects a randomization distribution PT and samples from that distribution. So PT is our distribution on possible actions. If you keep updating your LLM, PT would be your updated LLM from which you receive you sample the answer. And then you observe a reward, and we'll assume that this F star is the surface, which we don't know, right? And we only get to see a noisy version of that surface plus some zero mean sub-Gaussian ones. Now, I will assume in the spirit of learning theory that we have a model class F that contains F star. In other words, I'm going to assume that there is let's say, a transformer model that contains the true surface, right? So in other words, that surface up to these parameters of the crazy transformer, the form is known to me. One can try to relax this. This is kind of a to-do, but for now, this is the assumption that we're going to make. And I could have two objectives. One objective is called regret, which is over these time steps, I'm going to add up the suboptimalities of my choices drawn from that distribution PT at each time step versus the pi star, which is the maximizer of that red slice, right? Red function. Okay, so that's a regret. And essentially for the example of the doctor, it ensures that the doctor doesn't just explore but has to pay for all the suboptimalities along the trajectory, along the T interactions. As compared to what's called risk or PAC result, which is you get to do exploration as you wish, but then you output the final answer, pi t plus 1, right? So that's a risk. I'm going to be almost exclusively talking about the first one, but there are modifications that also give you the results for risk as well. So here the doctor gets to hurt a lot of patients just by only caring about exploration. And here the doctor has to really be careful about prescribing something that could hurt the person. Okay. Is the setup clear?
The pi star is optimal over the trajectory.
Second?
The pi star, is it optimal over the trajectory?
Pi star is the maximizer of F star.
Oh, then
It's just the maximizer. Yes. So going back. Pi star is just this point. It's the maximizer of this red curve, and we're only considering one curve, right? So there's just unknown f star, and we get to query at different points, and we would like to get as quickly as possible to the maximizer. And we keep paying for the gap to the maximum value we could have attained on this curve. Yeah. Other questions? Thanks. Yes.
What was the motivation for knowing the model class? The model.
Well, so a model class is our inductive bias, what we think the structure of the problem is. So I have to put the structure somewhere. So for instance, if you're doing computer vision, maybe the convolutional neural networks is that class F. You don't know the weights, but it's not crazy to assume that there exists a large enough convolutional neural network that will do very well. So here, it's not crazy to think that the doctor, so there exists some kind of a function that processes the context and then, like the history, medical history, and the current symptoms, and gives a prescription. It's not crazy to think that this could be an LLM, or a transformer. Okay. Other questions? Yes.
Maybe with the generalization of pi. So if I come from RL, should I think as each point there as being a Markov decision process, and I give pi and
each pi is a policy.
Yeah.
Yeah. Each pi is a policy, and we're having a distribution over policies. We're sampling one at random. That's correct. And the MDP is what is the whole process that goes into F star. That's the reward under the MDP. So there is an unknown MDP. And then this is the mean reward of this policy within that MDP. Yes.
So the decision maker chooses a distribution over.
Yes. Yes. Yeah. I mean, this is more general than just choosing determinants. So we'll allow distributions. Other questions? Thanks for the clarifications. And so the question is there a kind of a Vapnik-Chervenenko style theory? If you've studied the kind of the classical statistical learning, Vapnik-Chervenenko's dimension is kind of a classical notion of complexity that you give me a class F and it tells you what the sample complexity of the problem is, right? In the distribution-free-based learning. Okay, so a little bit more precisely, what do we mean by is there like a VC like quantity? What we mean is that we can write our objective, which is the expected regret of the decision maker, right? Which is this quantity, right? This is still a random quantity, by the way, because we have an expectation over pi t given the past, but then you have observations, and so this is still a random quantity, right? So we take expectation, expected regret of the decision maker, and now we can take the minimum over all algorithms and maximum over all unknown F star. The minimax formulation of the problem. You can also consider different formulations. You can talk about problem-specific, instance-dependent complexities and so forth. But this is the one that will. And so, what amounts to saying that I understood the problem, I understood the complexity of the problem. In my world, this amounts to finding some kind of complexity which lower bounds and upper bounds this min-max one, right? And especially if these match, then the algorithm that achieves this is somehow a minimax optimal algorithm. That's the best procedure for the worst case model. You can also consider a Bayesian point of view and so forth. Now, this complexity, so in the statistical learning setting, this would be like a VC dimension divided by number of samples type of thing, right? But here it's unclear what these quantities are. And I'm not just interested in kind of in math. I'm interested in understanding what is the algorithm that achieves this, because that potentially drives what new algorithms one can try. Okay, so let's talk about optimism. So there is a classical approach to a problem with finite number of arms. How many of you have seen UCB or multi-arm bandits? Okay, so almost all. So I'll go quick to them. That's great. So you have a finite number of arms. At some point in time t, you've collected these data by pooling the arms. On the vertical axis, you have reward. You can come up with the mean of the observed rewards. What you do is you take this mean, so f hat t is the mean of the observed rewards for the times when you pull this particular arm. You form you add to the mean, you add the confidence bonus. And this confidence bonus decays with the number of times you pull the arm. And this is called the upper confidence bound method. Right? So the upper confidence bound method is once you form this UCB, you take the largest value, the arm that attains the largest value of UCB. Okay. So why does optimism work? Just very briefly, we can now think about the continuous space of pi. It doesn't have to be discrete. So what are the essentials of this method? You form some kind of estimate of the mean, and you guarantee that there is a band pointwise over pi such that the unknown f star, that's the function we don't know, the mean reward, is contained pointwise in this band. So suppose that you're able to guarantee this. In that case, this is the solution to the UCB, right? It forms this. It takes the upper envelope and then chooses the largest value, the action that leads to the largest value, and then of course this is the optimal value, right? That's the pi star that optimizes this this curve, f star. So how bad is my regret? Well, because this is smaller than this value and this value is smaller than that value, what we have is that the gap is given by, this is what we've got. This is the value on f star that we got by choosing this pi t. So the gap is controlled by the width of the confidence band. So now the question is, can we guarantee that UCB shrinks this band over all the points where you query uniformly? The answer is yes, and in fact, this extends beyond finite arms. This extends to things like linear bandits. There's this classical, well, now classical method, LinUCB, about 15 years ago. This is the class F. These are linear functions. Pi is your decision, which is now a d-dimensional vector. Theta is the unknown parameter. This is the value. Let's say that they live in maybe a norm-controlled ball. And you can construct a confidence set, and then over this set, choose the best model and the best arm, right? So you're being optimistic here. You're saying, I'm going to choose the best model that's afforded by my data, right? By my confidence ball. And so this does work. And so it's natural to ask, is this the right principle? Is optimism all we need to solve our, per xt problem, per context problem on that red curve? And it turns out that it's not the right principle. It works if you have what's called bounded eluder dimension, but it fails in very simple examples. Yes.
What do you exactly mean by optimism?
So optimism is a class of procedures which construct a confidence set. Typically, this is based on some kind of regression with respect to past data, and then chooses the most optimistic element of that set, and then the best arm for that set. That is the class of algorithms. Maybe a little bit vaguely defined, but
They're related to some MLE or map or something.
yeah. So the way that you construct this confidence set is you find the maximum likelihood solution, and then put a ball around it in some way. Okay. So if you look at the notes that I posted on the first slide, that procedure is described there. Good questions. All right, so just look at these at this simple example. So my class F contains 3 functions. I don't know which one is true. So one of these mean reward functions is true. And I don't know, I get to select, sequentially choose elements pi, and then I observe a noisy value of one of them. I don't know which one, right? I need to kind of behave in a way that I quickly get to the maximum. So if this is the case, then this is a trivial problem, right? So whatever my VC dimension will be, it should say that this is a trivial problem because all the pi's, there exists a single pi that maximizes all the mean rewards, right? So this is a trivial problem. There's just one, no matter what the world is, it's always a good idea to I don't have breakfast in the morning, or something, have coffee in the morning. Right, so there's always a good policy. But now imagine that I shift them a little bit. Now all of a sudden this problem is difficult because I don't know which one is true, and I need to query. And let's suppose I get a Gaussian, observation with Gaussian noise. Then I really need to spend time here figuring out which one is the true maximum, and that incurs me a cost. So you see, simple shifts somehow matter in this problem. So it can't be just kind of covering numbers, right? That cannot be the answer. It's question of what is the complexity of this class. But now imagine that there is some kind of suboptimal action with a high signal-to-noise ratio. So what I'm illustrating here is that the gap between these is much larger than the noise level. And so if I query maybe once, I already know what is the true identity of the model, and then I can just maximize it, right? So that's like maybe in the medical example, the doctor can conduct one test that maybe is not good for the patient, right? Because the reward is not good. But then it brings a lot of information about what should be done, right? There is clearly some kind of information versus reward tension here, in that you can bring a lot of information by taking suboptimal actions. And that's not true for multi-arm bandit. For multi-arm bandit, because there is no structure between the arms, there is no dependence between the means of the arms in the multi-arm bandit problem, you don't have that. You don't have that. Does this make sense? Questions? Okay, so just to conclude, UCB fails because it just starts, it doesn't even look at these, right? It just starts concentrating here. Or maybe it queries once, but maybe it's not enough, and so it starts looking at the maximizer. Another way of saying this is you cannot always construct for any problem confidence sets that will shrink uniformly. It's just not feasible. There are examples of this form in the notes. We call this a defector example. Okay, so now comes a little bit more math, and instead of trying to motivate it, I will just present this complexity, and I will try to explain it carefully. So we call it the decision estimation coefficient, or the DEC. So I'll just refer to the DEC, decision estimation coefficient. And I'm going to assume that there is some kind of estimate f hat. I will come back to this later. There's an estimate f hat of the true f star. I'm not yet telling you what that estimate should be like. But suppose that there exists some f hat. So this notion of complexity will depend on the class f and this estimate f hat. And now I have this, what might seem like a horrible expression, but hopefully I can explain that this is not too bad. So I'm going to minimize over my randomization distributions P, right? This is the distribution from which I'm going to choose the action, right? This is my exploration/exploitation distribution, such that no matter what the true model is, no matter what the true f star is, I'm going to call it F. On average, over my draw from that randomization distribution, there is a relation between the instantaneous regret of making this decision as opposed to choosing the maximum pi star, right? So this is a regret of this decision on average. And the distance from the estimated value F hat. This shouldn't make too much sense, but or it shouldn't make sense why we're doing this, but let me try to kind of explain. There is a scale gamma here. That's a tuning parameter that we'll need to choose depending on some parameters of the problem. So sub gamma, this is the gamma parameter. Okay, this turns out to be an important notion for the problem that I described. There's a related notion, which we'll call the constrained DC, which is like a non-Lagrangian version of this, right? This is a constrained version. It says, choose the distribution, minimize over distributions over my choices, such that no matter what the true model is, I'm minimizing regret under my distribution, regret, a single round regret, conditionally, so this is subject to being in the epsilon ball around the estimated model I've had. Okay, so you can view this kind of as a Lagrangian version of this, right? Where you have a gamma parameter, where here it's a hard constraint epsilon. It turns out that this is nicer, and this is the right quantity. Although one can show the various relationships between. Any questions about this? Yes.
We were looking for min-max of the regret of the decision, right?
Min-max of
the regret.
Regret, yes. So okay. Let me say this. This is the quantity I'm interested in. I'm interested in finding these guys. And of course you can say, well, this is, take this to be that and that, right? So that's tautologically, right? So I want I want to have quantity that's simpler to calculate than minimum overall algorithms, which is, you know, a huge space, right? I can't even move around this space, right? So what I'm telling you is that I'm proposing a quantity that will be indeed involved in upper and lower bounds. That is a one-round quantity, right? Instead of like a T-round algorithm, right? Essentially what I'm saying is, here is a complexity notion that is one round, potentially easier to calculate. Right? Does that answer this? Other questions?
And you want that quantity to be computable or whatever, right? Like,
ideally, of course, and we'll see examples where this is computable and gives rise to new algorithms. There are other cases where non-constructively we can upper bound this, but there's still a lot of room in terms of computation.
so you're interested both in knowing the tightest bound, whatever, lower and upper bound, also an algorithm that gives you.
Yeah. Yeah. Great. Other questions? All good questions. All right. Okay, so and then if I take maximum over F hat, I'm not going to go into these details, but if you take maximum over this estimated model F hat in the convex hull of F, then this is the quantity that I will be using. Okay, so the result in this Forster et al. Paper in 2023 is that the Forster, Yanjun Han, and Noah Golovich, is that this complicated object is lower and upper bounded by this DEC quantity that I just described, except that there are two scales that differ. In the lower bound, the scale is 1 over square root of t, and in the upper bound, the scale is some quantity which I haven't yet defined over t, square root of st over t, right? So up to this difference in scales, you kind of get what we want, and these are perhaps the first lower bounds for genetic problems of this type. And a similar statement can be made for risk instead of regret. So that's the final point. So you get to explore and then make the final decision.
Okay, let's go back. So the definition of PhD.
Yes. So it's what I described is in terms of this one, and our initial papers were in terms of this quantity. But just think of this as a Lagrangian version.
What is your initial F hat?
Initial F hat is nothing, and I will tell you how to build F hats and what they should satisfy. I haven't yet.
The lower bound was after running this. So what's the lower bound? Is with respect to some F hat, or
The lower bound is this complexity, which is just the complexity of F.
okay.
So think of this as a VC dimension of F, if you wish. Right? It's the complexity of solving this problem. Yes.
Do I understand correctly? Under those while assumptions, if I tune gamma in a good way, then the estimation error become negligible, right?
It's not negligible. This has been so the difference between the upper and lower bound could be large, and this has been kind of a we spent several years in trying to eliminate it, and we're almost. I'll show you a result which almost does it. But this is 2023, circa 2020. Okay, good. All right, so okay, just like in the VC dimension, you can plug in linear classifiers, you can plug in whatever classifiers, you can calculate it for different problems that people have studied, right? So if you take a multi-arm bandit, this DEC behaves as at scale epsilon behaves as epsilon squared of A, and that leads to regret of A squared of T. Now, the correct one is actually square root of AT, so this is square root of A away, and that's the culprit here is this estimation. Yeah. But we know how to remove this and get square root of AT. For linear bandits, this VC dimension is epsilon times square root of the square root of D, the dimension of the arms, and the regret it correctly scales at D squared of T. So in this case, it gives correct upper bound. So that already shows you that there is no way just by DEC to disentangle these two situations. In general, for parametric classes, it's often the case that DEC behaves as epsilon times square root of some kind of effective dimension of the problem. But then you can also look at non-parametric bandits, for which DEC behaves differently, and then that leads to regret both upper and lower bounds of this form. D plus 1 over D plus. These are slow non-parametric rates. But also you can get fast rates if DEC has this threshold behavior, which is the case for those three functions with a cheating arm, where the arm brings a lot of information. You have this type of behavior because you just need to pull that arm and then go to the maximum. Okay, so I'm going to show the upper bound just trivially in terms of offset DEC. So let me just remind you, in terms of this version, even though I showed the result in terms of this one, it's easier to get the upper bound for this version. Okay, so what are we gonna do? Regret is this just by definition, right? This is my definition of regret. It's the expected cumulative over time, expected suboptimality of my decision versus the maximizer. Yeah, good. All I'm gonna do is add and subtract the square distance between f star and f hat t at my decision pi t, averaged over pi t drawn from randomization distribution pt, right? And then I have to put it back. So this is what SQ is. That is this quantity that I did not define on the previous slides. Now, if the randomization distribution for your next action, the PT, is obtained by solving the min-max problem in the definition. So if if on each round, given f hat t, I solve the minimum for pt, then this quantity is upper bounded by DEC at every time step. So I get t times DEC plus this, and then I balance gamma. That's it. So the upper bound is trivial. But the notion that this can be controlled is perhaps non-trivial. What is this estimation error? It's a kind of a weird object. Why? Because f hat t has to be computed before round t, before round little t. So that estimate needs to be done with data up to t minus 1, because I need to solve for that min-max problem, and that requires f hat t. So then this error is on this f hat t, which is measurable with respect to 1 to t minus 1, but evaluated at my decision pi t, right? Now, how can we ensure that this is small? That's a bit weird because, okay, this is a regression, some kind of, you can think of f hat being a solution to a regression problem, but like what kind of guarantee can we invoke for this? How do we update f hat t? If you come from statistics, what you know is that the f hat t, the regression solution, can be close to f star either on fixed design data, if you just have fixed design x's and they're not changing, or out of sample if all the data came IID from that distribution. Okay. But how do you get this? Okay, so let me pause that question for one slide and just summarize what I said. Suppose I can compute f hat t from an online estimation algorithm. Then I plug it into the min-max optimization problem, which is this, or the constrained version. And then I just sample from that randomization distribution. So this is the template. We call it E2D, estimation to decisions. Any questions about this?
Is that solvable?
Are you asking about computation?
Yeah.
It depends on F, the class F. There are cases where it's solvable and cases where it's not.
Then what's the advantage of using this framework?
Okay, so there are two questions. One is, can this be done? Understanding statistically whether this problem is, what are the inherent complexities of this problem? And then the other one is, if I have limited computation, can I solve it? So, and these are disjoint problems, right? So just like in statistics, statistical learning, you write down MLE, I can't always solve it, right? It depends on the class. But the fact that MLE has some properties is an interesting statistical question. So I will address the computation as well in a few slides for some problems. Yes.
So I don't follow why estimation, giving a bound for estimation error is not trivial.
Yeah, because it's not trivial because pi t is a sequence that I choose. The sequence of dependent random variables depends on the path. So I'm trying to get a denoising error or regression closeness.
And we don't have any sort of Markov structure, right?
I can depend on everything in the path. Yeah, my randomization distribution depends on everything. Good questions. Okay. All right. But the template is clear, right? Okay, so this is where online regression comes in to rescue us. Online regression says that you can actually denoise an arbitrary sequence, even if it's adversarially chosen. So even though we're choosing the sequence ourselves, the choice is so complicated that we might as well just throw the baby with water and just say it's an arbitrary sequence. So you have an arbitrary sequence, you sequentially observe noisy values of the function at pi t's. There's a conditional independence of Gaussian and f star is in the class. And the claim is that there exists a sequence of estimators. There is a way to construct these f hat t's such that this estimation error, the problem of interest, for a finite class is bounded by log f, log cardinality of f, if you're working with a finite class, or you've done discretization. That's kind of the first step in any problem. You want to understand what happens for a finite collection of models. And more generally, we understand that there is some kind of sequential complexities. This is a subject I've in my co-authors studied 10 years ago. And moreover, this guarantee holds for arbitrary sequence, even if it's adversarially chosen as you go. If there is no noise, if epsilon t is just a noiseless value, what gives you log f is what's called a halving algorithm. If you do have noise, then for finite class, it's exponential weights algorithm. Many of you probably have seen this due to Vovk. You can read Chesebianski-Lugosi. In general, okay, you can look at this paper in 2014 for what this object is. It's kind of a local Rademacher complexity, but the sequential one. Mm-hmm.
Like this exponential weights, that would be then linear in the size of the class.
Yes, so computation could be, yeah. So at this point, I want to avoid computation. Yes. I think there's a huge amount of work to be done in terms of computation.
Is there any dependence on capital T in the operable?
Yeah, no. So if you were to divide by t both sides, so this would just say that the average regret has a fast rate of 1/t. Well, yeah, 1/t. Yeah, because so if you go to exponential weights algorithm of Littlestone Wormuth 94, that sets the step size 1/square root of t, and then you get square root of t rate. But these are what's called the mixing losses. So for log loss or for squared loss, you get fast rate 1/t. Good question. Thanks. Other question? Yes.
So if the pies are arbitrarily sequenced anyway, couldn't you do it with the pies that result from, say, UCB or some other type of algorithm? Like, if it doesn't matter what the pies are anyway?
It doesn't matter for this, but it matters for the first part. So here it doesn't matter. You're right.
Right.
But UCB will not minimize this, except for this finite arm case or linear bandit case. UCB will not ensure that this is small.
Okay. No, I think but my question is sort of like, can't you decouple the two problems of estimating the function and achieving low regret? Because you could do a UCB to achieve low regret and get the square root, like the standard bounds that you get.
Yes, but I think the answer to your question is UCB scales with the number of arms. And the minimax regret is square root of size of pi, right? So you cannot work with continuous decision spaces or large, right? Yes. So maybe I didn't say this, but my kind of what I want is something that does not depend on the cardinality of pi, because my decision space, because that can be a very huge. Think of LLMs, right? My answers to problems. 5 minutes. Okay, that's excellent. I can go over longer time. Okay. So, all right. So, okay. Then there is a question of computation, and I will just show you one result, which is actually historically is what we started with. If we do have finite number of arms, pi, but there is some class f. It's just unstructured over the pi's. Then this has a closed form solution. We don't need to actually solve it exactly, but in this particular case, it has a closed form solution. So let me just present this. This is the contextual bandit result from 2020. So again, we receive a context, we make a decision, we observe reward, and we assume that the reward is a noisy version of making that decision in that context. Okay. So this is the model, right? And it turns out that there's a closed form solution to the minimax problem that I described. We call it the inverse gap weighting distribution, and that leads to the square CB algorithm. So again, we estimate f hat t using online regression. This is the closed form solution to that p. Okay, you can take derivatives. It's very simple, this gives you, if your online regression method is minimax optimal, it gives you a minimax optimal for this result of this problem.
Now we are worrying about efficiency or not.
No.
Okay.
Well, okay. The solution to this DEC is efficient because
But you would like to write down the probabilities of all actions with the action spaces. You would like to sample, I guess.
I would like
Explicitly
I
write
would like
down
to sample
the-
from this distribution.
Yes.
Okay, but okay, I think I can do this. Yeah. Yeah. Again, I think there is a lot of work to be done, kind of in making these solutions efficient in practice. Yeah. So a lot of people do Boltzmann sampling in practice. They estimate the model using regression, treating data as IID, and then do Boltzmann sampling on top to do some kind of randomization. This is a optimal way. This has been implemented now in this decision making without confidence or optimism. It's a great motto. This is part of this WOPL-WOBIT. We ran it on a bunch of experiments, and it does very well in practical applications. Questions? Yeah.
I have a dumb question. You said, that distribution has a closed form.
Yes.
Lambda is not specified.
Yeah, lambda has to be chosen to balance the two terms, which you can do if you know your class F.
Sure.
In principle,
Yeah.
in practice, we do it by cross-validation.
But it's not like simple normalization.
Yeah. We do it by cross-validation. Okay, so let me spend 5 minutes to talk about this general setting. So this is just to let you know that this is in fact a tip of an iceberg of a bigger problem, which is the following. Feel free to zone out. So there is some collection of models. There is a decision space and observation space. There is necessarily no reward at this point. And there is some loss functional from a model and a decision into reals, and there's unknown model M star. In some sense, this is a simpler problem, a simpler formulation. So for T rounds, the decision maker selects a decision and observes some observation drawn from a distribution M star of pi t. So this collection of models is a collection of distributions, conditional distributions given pi t, given pi. Very, very abstract. And one can still define a regret and this a pack notion or risk for the final output. And if you've studied statistics, if you've studied decision theory, classical decision theory is just a one round of this. You get to interact with the model. You get some observations. Your decision is an estimator or a hypothesis test to perform, and then you get an outcome, and then you estimate the model. Okay, but this is an interactive version. So okay, I already said this, and it subsumes multi-term bandit, structured bandit, contextual bandit, episodic reinforcement learning, but also includes statistical learning, right? So you can define a loss function of a model and an estimator as kind of this excess loss, something that we like to do in learning theory. Statistical estimation, this is the loss function. It's how well you estimate the parameter of the model. You can talk about estimation of linear functionals. This is a subject that has been studied in statistics. Okay, there is a classical Donoghue models of continuity that characterizes problems of this type. Okay, and 2 minutes. Okay, so one issue is that in the lower bound, Okay, this is for those who have been playing with such quantities. How do you construct lower bounds in statistics? In statistics, you take two models which are close in some TV Hellinger or whatever distance, so they're hardly distinguishable. But if you make a mistake of choosing the wrong model, then you incur a cost, right? So this is a two-point method. A Fano method, Fano inequality, says that I'm going to pack my space with many models, and I get richness of the class of models. The DEC method, you can think of this as an interactive version of a two-point method. In fact, the way that the lower bound proceeds is you fix a model, f hat, then the DEC itself tells you what the alternative is for the fixed algorithm. You fix a model, fix the algorithm, and then that gives you the alternative because of this interaction. So it's already a departure from classical kind of statistical approach. The choice of the alternative depends on the algorithm itself. So what we've been missing for a couple of years is kind of the how to get the richness of the of this class of models. And this is seems to be one way of doing it. And this is what we call a fractional cover of the class of models. And it is a similar form, but as DEC, it's an inf over randomization distributions, sup over models, how much mass, 1 over how much mass the randomization distribution puts on near optimizers, where here it's a loss, so we're minimizing near optimizers, delta minimizers of this L. Indeed, one can see that it's a relaxation, a continuous relaxation of a notion of a cover. Let me say that first, for bandit problems, it already characterizes, even with exponential gap, it characterizes the sample complexity. So T star is just how long you have to wait until regret drops to below delta. It's the same way. It's an alternative way of talking about rates of convergence. So it characterizes, even though there is an exponential gap, it characterizes whether a certain bandit problem is possible. This was an open problem for a while. But you can actually put it together with the decision estimation coefficient. So now, because we're talking about, we don't have necessarily rewards, but generic observations from a model, we have to talk about Hellinger distance. We replace the square distance by Hellinger distance. For Gaussian rewards, this is equivalent. Distance between models is just squared between the means. But this is the more general notion. And one can show the same, one can show the same result as I showed before. But now we can put it together with this fractional cover, and I'll stop after this, is that the minimax complexity of the problem, the sample complexity of the problem, can be expressed in terms of maximum between these two quantities and the product of almost the same quantities, where the TDC is exactly the same. It's the epsilon such that DEC drops below delta. So this is almost tight characterization up to square root. So this is a sum and this is a product. And one more thing is that this is a convex hull of the models, and here it's not a convex hull. So there are two issues. But for if the class of models is convex, then up to square root, this resolves the issue that I was mentioning. Okay, it's related to some quantities in classical statistics. And kind of in this recent paper with Fan Chen, he shows that there is a relationship to SQ dimension and statistical query models, which might be of interest to computer science audience. In fact, SQ dimension is very closely related to DEC for a specific setting. There is a way to express differential privacy in this setting and robust and smooth learning. Okay, so I think I will stop here. Hopefully I told you a story where one can decompose the decision making into estimation exploration. There's a course and course notes that you can follow. Thank you.